Welcome, ladies and gentlemen, to this exercise. In this exercise, we are going to make this flow sheet, which will consist of a seg mill, trommel, a splitter, hydrocyclone, and ball mill. This is a SABC. So we are going to look at feed tonnage of 2,292 tons per hour with these specs, and the final product size is P80 of 140 micrometers in the overflow of the cyclone. And the feed is going to be crushed material feed with the particle size that is shown here. This is the feed particle size data. We're going to make the water addition to achieve 70% in the segment. So we're going to have water addition so that we satisfy this condition. And for the pebble crusher, we're going to use a 13mm CCS, and we're going to use the model 430 semi-autogenous mill in JKSimMet for the seg mill with these parameters. So these parameters, they are obtained from test strokes that are done on the process. So first of all, we're going to look at how we model this circuit in JKSimMet, right, being guided by these specs. So the first part is we're going to lay out this flow sheet and input the process parameters. So I'm going to open my JKSimMet. I'm using the latest version of JKSimMet, version 6.31, for this exercise. So we're going to have our feed, we're going to have water addition. For pebble crushers, we're going to use a cone crusher. Then we add our mill, autogenous mill. We are going to have hydrocyclones and two products splitter. And a sump. So let me just make them arrange them in a way that so going to connect the flow sheet. Then I'm going to add a trommel. So under screens, I'll need to add trimming. So it's going to feed into the sump. So we're going to add also a bore meal. And another hydrocyclone. Then let me rotate the bore meal so that the cyclone underflow feeds into the bore meal. Then from the bore meal discharge goes into the sump. So we're going to have water addition into the bore meal, water addition into the sump, and water addition into the segment, like what we've already done. So we will need water addition, to the sump, as well as water addition to the bore meal. So let's include some arrows and increase the lines thickness. I'll use 1 point, and blue for water addition. I would rather use dotted lines for water. Right, so now we can make some additions on the equipment for now. Right, so we need now to, let's save our work. So now we need, if we check the flow sheet, we need to define the system properties. So this is solid specific gravity of 2.7, the liquid specific gravity. So we don't change these parameters. Then we have to look at our sieve series, right? So by default, this will be the master sieve series. But looking at the data that we have here, our top size is 270, so we're going to make it 300 as the top size. Then we copy this data, so 300 is going to be our top size. Then we paste the data, then you say apply, you accept wipe data. The master 6 is modified. All streams data apart from experimental will be deleted, so just accept this, say okay, and you apply. Right, so we are now able to define our feed. So we use the survey data. Right here you can see all the streams in the flow sheets making up columns. Right, here's the autogenous meal, load, feed, we got the corn crusher product, autogenous product. All these, they represent the streams. Right, so just to show you where these streams, the naming is coming from, let me just close it and make these additions. Right, so I want to define the data for the feed. So I want to define data here, right, in this column. So our flow rate according to the exercise is 2292 tons per hour, and 100%. Then the feed, we copy this data. So we have to note that this is cumulative passing, right? So here we have to input cumulative passing here. Then Control V to paste the information. Then you need to transfer this information into the flow sheet. Right, so you see that they just create a graph. So we just want to check if the data has been transferred to feed stream 1. So you can see this is the data. case. So this is the data that has been brought into our flow sheet. So we're going to make some addition of other streams, but for now we want to configure the flow sheet information. So we're going to see if we get a P80 of 140 micrometers on the overflow of the cyclone. So water addition to the SABC is for us to achieve 70% in the SABC. So we're going to configure this water feed, right? So if you double click it, you have two models. The first model is to water feeder required percentage solids, and the second model is the water feeder water addition. So this one is for calculating the amount of water that we need to add, and the first one here is to come up with a desired percentage solids in the discharge. So according to our instruction, we want to achieve 70% solids in the SABC. So I'm going to choose this one, then I'll put 70%. Then I'll close it. On the Pebble crusher, using the model 400 with 13 millimeters CCS. So then double click this. So I input 13 millimeters. So I've used the crusher Anderson Whiten model. For the SABC, I will use model 430. Okay, so I'll configure node 1, 2, 3, 4, and 5. So node 1 I will not change. That's 1.160. Node 2 is 4, and negative 0.91. Node 3 is 0.750. Negative 0 point, sorry. Node 4 is negative 0.03. And node 5 is 0.330. So we've completed the fracture rates in breakage for the 5 nodes. So we're going to enter the values for the drop weight test parameters. So like I've highlighted before, these parameters, they are obtained from experimental test works that will be done for the combination circuit. This also includes the drop weight test work, and all the other extensive or test works that are done for the process. So the segment is a bore filling of 18% by volume. Okay, so we look at the trammel. I think these ones, they are not, this is not part of the exercise. Let me just delete it. So the trammel parameters, we have to configure them. So we're going to use model 211. So you see there are four models that we can use for the trammel. We've got the single component efficiency curve, whereby you can specify these efficiency curve parameters. We've got single component efficiency curve. We've got the splined efficiency curve. We've got a simple two-way splitter model trammel. D50C at 3 millimeters. Okay, so let's choose the best. So here we've got water to the cyclone box, feed box, 53% solids. So this is water to the cyclone feed box. Okay. Now, so for the ball mill, the rotation speed was set to 4.5% of the critical speed. So let's open the ball mill. So again, for the ball mill, we've got the two models. We've got perfect mixing and size converter, but in this case we want to use ball mill perfect mixing. So the first parameters, the rotation speed is 74, zero point 0.74, zero point 0.745. Okay. Yes. A work index of 14.1. Diameter of 6.7. Length of 11.1. $58.8 for mill charge. So these are going to be two mills in parallel. Okay, so we've configured, but we want to also configure the water feed so that the percentage solids will be 72% from the ball mill discharge. So yeah, 72%. So for the splitter, we've got three modules: simple two-way splitter, water and solids two-way splitter, fixed two ways of volume splitter, right? But in this case, we want it to cut to one toward the top. Let's see which will be the best model. So I think we have used the okay, so we're not going to change much here. We've just configured to cut one towards top side. Then for the hydrocyclones, percentage solids in overflow should be 31.76%. P8 overflow is 140 micrometers. You have to indicate it cyclones in parallel. So we have got different modules here, so we have to look for the best one to use in this situation. Percentage solids, percentage underflow. Okay, let's look. Okay, so for this one, we are going to make use of a model to encompass solids in the overflow and in the underflow. So the best model will be the water and solids two-way split for the cyclone. So the fraction split to top product, which is the overflow, 31.76. So the desired P80 is 140 micrometers. So let's look if we are able to achieve this, or we just use the default parameters. Okay, that 1.76, and I use the other default parameters. We can as well, during the simulation exercise, change some of the parameters of the model. So we can now run the model. So to run the model, go to flow sheet. We need to run the simulation first. So it's reporting that the autogenous mu predicted total mu load is impossibly high and is not reported. And there is also prediction for roping of the hydrocarbon. Right, so you can as well view the results. So we start with the feed. Gasha product. So I'm just going to bring all the streams for graphing. So this is the feed. Let me so to make it clear, let me bring in the information boxes. Don't know why my software is crashed. So we are going to insert the design boxes. So we still have the autogenous mu predicting top mu load is impossibly high and is not reported. Total mu load, the predicted total mu load is impossibly high and is not reported. And also the hydrocyclone let us check if we have configured the segmu correctly. Okay, so 1.160. It's not 2, negative 0.91. So 5. Negative 0.03. And the last node 5 is 0.33. So the bomb filling is 18% by volume, and power fraction to critical speed. Of 0.78.